All right, welcome back. Let's go. Let's start with the last presentation of the day, the last lecture of the day. Karen Crowther from the University of Oslo will be presenting a lecture called Principles, Holography, and Infinity in Quantum Gravity.
Thanks. Well, that's the title for both lectures together. For this first lecture, I'll just be starting with some general motivations for looking at principles in quantum gravity in the first half, and in the second half, I'll talk a bit about holographic principle and entropy balance in quantum gravity. And then for the next lecture tomorrow, we'll be looking at singularities and their role, singularity resolution as another principle of quantum gravity. So starting with the motivation for looking for principles.
Yes. Attach this somehow.
All right.
Thank you very much.
So Wheeler said, no question about quantum gravity is more difficult than the question, what is the question? So yeah, what is actually the problem of quantum gravity? So normally when we're looking for a new theory, it's because we've had some observed anomaly, so empirical phenomena, that's not being accounted for by our current theories. So we had the black body radiation, we had the photoelectric effect motivating quantum mechanics, we had famous asymmetries in Maxwell's laws not being observed in nature, which motivated special relativity. But now, quantum gravity, we don't have these kind of anomalies. Instead, we're being motivated mainly by conceptual dissatisfaction, philosophical concerns, and theoretical problems of our own construction. So, problem, we don't have these observed anomalies, we don't have theory, but also I think the problem is that we don't really know what the theory should be like. What is it actually supposed to be doing? So instead what we do have, of course, is a plurality of different approaches to quantum gravity. And they're all doing very different things. They're adopting different criteria of success. So we can think of quantum gravity as being a theory that satisfies whatever kind of criteria that we lay out. Once we find this particular set of principles and constraints, we can find a theory that satisfies those. That would be quantum gravity. So looking for these principles and constraints. So starting by looking at the various motivations, why we're looking for this theory, and what we expect it to actually be doing. And then kind of turning these around, using them as principles in different roles in theory development. And then we can philosophically assess these different principles and see what they entail, how they relate to one another, whether they're actually well motivated or not. So for this one, I'll start by first giving some background of principles in theoretical, physical theorizing, and then look at some motivations for quantum gravity. I won't come to the actual constraints at the end. It's already going to be a bit much. So starting by looking at some previous episodes in physics, theory change, and the roles of principles, asking where our principles come from, and how we might evaluate these. So in times of crisis, it's happened before, it's happening now, physics tends to turn to re-evaluate its principles and also to seek new ones. So let's now take a trip to the 1904 World's Fair in St. Louis. We've got a big wheel, we've got an airship, we've got all sorts of new foods. This is the very first ice cream cones. We also had the very first fairy floss, we call it in Australia. It's like cotton candy in America. This is an elephant made out of almonds for some reason. But like, So I originally only meant to include one slide on this, but like the more I looked at it, the more insane it got. So I couldn't find the Swiss Alps or the French Alps, but here are the Tyrolean Alps. So they, constructed these artificial mountains 100 feet tall, but also they had, reconstructions of English castles, had Japanese tea gardens, Chinese emperors' palaces, all kinds of stuff. They had a reenactment of the Boer War. They had the third ever Olympic Games, which I put a link there, and I encourage you to read it because that shit was like crazy. But of course we had a lot of technological and medical innovations as well. So some of the first X-ray machines, also the very first infant incubators. And here in the Hall of Industry, the General Electric Company has this huge 3,000 horsepower steam turbine. Also some not so good, this one's good actually. The Palace of Electricity. And you can see some of the crowds, lots of people here. But yeah, also some not so good things. Human zoos. This Filipino exhibition was just massive apparently. You can see it's 47 acres, 6 different villages. This was part of the Olympic Games, just to give you a hint there. Also, I did find the French exhibition. So this is the French Salon, and a fine selection of French automobiles here. So, okay. See, we've got the whole kind of world at our feet. This great era of technological advancement, everything's happening, and yet you all know we're here, kind of on the cusp of physics. So what are we doing here? Well, we're of course here for a great scientific meeting. So under the Normative Science Division of the International Congress, in the section on applied mathematics, they invited Boltzmann and Poincaré to give lectures. And the Poincaré lecture is titled The Present and Future of Mathematical Physics. And this one is much discussed because it really puts very clearly the problems being faced by physics right then. And he comes very close to articulating special relativity. But in this paper, he describes 2 crises in physics. The first one has already passed. It showed basically that Newtonian-style laws, meaning ones being differential equations with a central mass, they were found not to capture the full range of phenomena. So thinking about the development of electrodynamics here. And he argues that this crisis, in trying to resolve it, we turn to principles, and what we have now is physics of the principles. So he thinks we abandoned the thought of exploring kind of the micro details of the universe, isolating the parts of this vast mechanism and analysing one by one the forces that set them going, and instead we turn to these general principles, kind of relieve us of having to do all this detailed work. It's because, of course, we didn't have access to what's actually going on, but we can look at the phenomena and get these general principles to get us new physics, to get us truth, without needing to know the details. So these are the principles he lays out. Principle of conservation of energy, second law of thermodynamics, Newton's first, I guess. Principle of relativity, conservation of mass, principle of least action. And he thinks from these we can get the whole of physics. And as I said, Maxwell's theory is really held up as kind of the pristine example of this new modern physics. And yet, this beautiful physics is now itself going through a crisis. We're now entering a second crisis. And what he does is in the paper is he shows that each one of these principles can be thought of as under threat from these new observed anomalies, being Brownian motion, radioactivity, Michelson-Morley experiment, and experiments, accelerating electrons to very high energies. But yeah, notably, he doesn't mention black body radiation of the photoelectric effect. Kind of thought those were experimental glitches or something. Wasn't so concerned about them. But of course, just as he's doing all this and laying out all these problems, we all know what happens very next year, is that Einstein comes along and solves many of these. In his famous 4 papers, photoelectric effect, grounded motion, special relativity, and mass energy equivalence. So tying together some of these principles. And later on, in 1919, had I think it's a newspaper article, he basically makes this same distinction similar to what Poincaré did, saying that on the one hand we can distinguish between constructive theories, where we start off with the detailed description of the micro constituents and then build up our phenomenological laws. But on the other hand, we have principle theories. And these are the ones that we start with general principles and then use those to construct the laws. So we tend to turn to principle theories, again, when the details are obscure, of course special relativity being held up now as an example of this. So, yeah, are we now entering a third crisis, or already in it? So does quantum gravity represent a crisis like this too? Because again, we have many principles from our current theories that are apparently under threat, but they're not under threat from observed phenomena anymore. It's really coming from the theories themselves. Our best theories of physics, the ones that kind of came out of that second crisis, are causing themselves problems to their own principles. So maybe we need a new principle theory. And yet, most approaches to quantum gravity might be seen as constituent theories, trying to find these basic building blocks of space-time. So, yeah, this is the open question here. So thinking then about the second speaker from the 1904 Congress, what did Boltzmann say? So of course he's developing his kinetic theory, and so I did dig for this. Everyone's discussed the Poincaré paper. No one's really discussed this one, and I found it luckily in a biography of his. So his talk was reluctantly titled "The Relation of Applied Mathematics." Why? Because they didn't let him speak in the physics section. They put him in the mathematics section, thinking that this kinetic theory is just, a nice way of deriving things and not really physics. But he says, I'm not actually a mathematician, I'm a physicist, and one day you'll recognize theoretical physics as a legitimate field. Yeah, and most of the other physicists there weren't really convinced by his theory. They were really still into the Maxwell's theories, replacing this mechanical worldview of Newton's, that first crisis. Or else they favoured this phenomenological approach using general principles. In either case, they were very hostile towards Boltzmann's views. So, kind of a 10-point summary of what he said in the paper to try and defend his atomic theory. Says science needs bold hypotheses. The atomic theory is a bold hypothesis. Even continuum theories, they use hypotheses, some speculation. And the atomic theory helps us understand kind of more stuff than the continuum theory. Again, even our electromagnetic theories, we're talking about electrons there. And also the reality of atoms and electrons is strongly supported by this recent evidence, but it hasn't yet been actually demonstrated. So, continuum of that, trying to respond to these accusations that he's just doing some crazy metaphysics beyond science. Just trying to tell us, we shouldn't really be relying on these kind of laws of thought, these kind of Kantian a priori assumptions and things like this, just as Chris was saying in his last talk. So he thinks future philosophy should avoid speculative question and change laws of thought so they don't interfere with scientific theories such as the atomic theory. So, yeah, and I guess you probably know what happened to Boltzmann after this. He hung himself 2 years later, probably because no one listened to him, just before we did get this evidence from the new theories of radiation to confirm his theory. So again, coming back to our question, does quantum gravity represent the third crisis? We do need to evaluate our principles. We do need to seek new ones, I think. But now we can also recognize this third pillar of modern physics regarding the entropy, microstates, thermodynamics, and maybe the constructive approach as well. And maybe this can also help us solve the crisis. So, what is a principle? Why is it important? I take a really broad definition of principle as being kind of anything that's used in physical theorizing, that's being used to help us define our theory. Sorry. So, as I said, they've always played a role, particularly in times of crisis. So, yeah, we can try to look for appropriate guiding principles and postulates to help us find a theory that satisfies the constraints that we expect quantum gravity to satisfy. In quantum gravity, the principles, they're playing a much bigger role, I think, than in previous times because of the lack of experimental anomalies. They're being used this time not just heuristically to kind of motivate and guide the theory, but also as a means of confirmation. So if our new approach satisfies or is in accordance with the principle, then this is taking a strong indication that you're on the right track. So I think we should look at the principles, kind of better understand what's being sought, what we count. It'll help us in evaluating the different approaches, but also to help us get some guiding principles down, see where we're going. So, several different roles of principles. Okay, that slide's a bit messed up. First, principles can play a role as guiding principles, which means that they're used primarily heuristically, but may or may not be actually retained in the full theory. You can think of something like Mach's principle in relativity. On the other hand, you could lay it down as a postulate of the theory, so just starting off with this and taking it as core of the theory. You might have principles used as criteria of theory acceptance. So this is like a strong constraint, meaning that the theory will not be accepted unless it's shown to satisfy that principle. And here it might be taken, so these roles aren't exclusive at all. It might be taken as part of the definition of the theory, or it might be an external constraint, coming from other theories or from the world that you nevertheless have to match up to. And, okay. Yeah, that one's a bit messed up too. Also used as means of confirmation, as I said. And here it might be expected, so meaning if it's already played a role in, as a guiding principle, postulate, or criterion. Nevertheless, if you're satisfying that theory, it's satisfying that principle, it's still serving as a means of confirmation. Or it might be unexpected, so kind of like a prediction. You have the theory, and it's turned out to satisfy this principle, and you take it as a good indication that you're on the right track. So many different roles of principles in theory development here. So some examples here, you can think, for instance, in loop quantum gravity, got quantization taken as a postulate, got background independence being taken in many different roles, guiding principle, criterion of perception, means of confirmation, discreteness as a criterion, UV completeness as a means of confirmation. You can think of causal set theory, which takes discreteness as a postulate, and yet uses Lorentz invariance, consistency, as kind of a guiding principle and also a criterion of acceptance. And of course, string theory, taking unification as a criterion, that's trying to be a unified theory of everything, and yet also by showing that they've achieved that, that's taken as a means of confirmation upon the new theory. So how do we evaluate our principles? So Niels and I wrote a paper examining the principle of UV completeness as a principle of quantum gravity. So to do it, you need to do it taking into account the particular roles. So starting off, as a criterion of acceptance upon the theory, and then going through all these different assessments, and then looking at it as a guiding principle and going through the different assessments. So looking first at kind of the general physical motivations, where's it coming from, what's it supposed to be doing, some general philosophical motivations, why is it philosophically desirable, and its consequences, links to other principles, so how we can construct these different webs of principles, how they match up with one another, do we have contradictions, what are the consequences of linking it up with different principles. And then also, of course, looking at the particular approaches. Is it necessary in that particular approach? Is it doing what it's supposed to be doing, or do we not actually need it there? So different ways of evaluating our principle. It's just kind of a picture of how you might want to put the webs of principles together. And of course, you can have different webs with different principles. Okay. So where do we find our principles? Well, we could have metaphysical assumptions or a priori considerations, which, as Boltzmann said, probably best to avoid, as Chris said as well. We have empirical phenomena. We might be able to find principles there that we can elevate from the phenomena. We have our current theories, which have their own principles. So do we seek to preserve those? What roles would they play in finding a new theory? But then we also have theoretical results, problems or strange predictions that seem to be coming out as we're attempting already to combine our theories. So, yeah, interested in principles that are really kind of motivating the new theory, as well as the ones that tend to constrain it. So mainly kind of these two, the current theories and the new theoretical results. So yeah, now turning to the motivations for quantum gravity. We have, I think the main thing here is having a complete coherent explanation. And this comes from looking at kind of external consistency between GR and quantum mechanics, but we also have internal problems, so problems within GR and quantum mechanics themselves separately that seem to motivate a new theory. And then, yeah, we have theoretical problems and striking theoretical results, and we'll try to get through these in the rest of the lecture. So the primary motivation for quantum gravity is this external inconsistency between our two theories. Both GR and quantum theory are supposed to be fundamental, universal theories applying to everything at all scales, and yet they're saying conflicting things about the world. which luckily for all practical purposes we can ignore, except that we're expecting to need both for describing some parts of the world, of course, namely black holes and very early universe cosmology. So it's this external inconsistency, meaning it's between the two theories together, that's really motivating us for the new theory, but also giving some constraints on the new theory, where we're looking for a theory that takes into account somehow the insights of both our current theories, but also applies in this particular domains where we're expecting the theory to be necessary. So yeah, it also gives us some constraints as well as motivating the theory. So I'd say that's what's really underlying this and why we're not satisfied with this two competing pictures in a way, is because we do kind of want a coherent fundamental picture of the world. We want complete coverage of everything, complete explanation, even of these domains that we can't directly access. And I think this kind of more basic goal of physics of giving us complete explanation is also behind some of these other, the reason why we're viewing these problems within our current theories as motivations for a new theory. So yeah, we have internal problems with GR and quantum mechanics, quantum field theory, that are typically expressed as being motivations for quantum gravity. Namely, the space-time singularities in GR, measurement problem, quantum mechanics, also divergences in quantum field theory. And in each of these cases, there's this feeling that the theory is somehow incomplete, that it's missing something, and so we want more. We're looking then for a deeper theory. So in the next lecture, I'll be discussing the singularities and divergences. But yeah, those are problems within our current theories. We also have problems when we're attempting to combine our current theories. So in semi-classical gravity, QFT and curved space-time and so on, once we put them together, we end up with these weird problems. So we have UV incompleteness, lots of issues in semi-classical gravity. You can talk to Eric Curie about that. Black hole information paradox, talk to David about that. So looking at these, can ask, well, really, in what sense are they motivations for the new theory? Because they're not empirically motivated at all, and nor are they coming from our best well-established physics as we've used those theories, right? It's coming from very speculative, purely theoretical attempts to combine them together. So it's kind of problems we've made up along the way, really. And yet we're taking this, of course, as kind of indications of where to look, things to work on. So it's worth looking deeper again and saying, well, how and why and should they motivate theory, and what's the consequence of these kind of principles? Right. So I would say that they're only problems to the extent that they prevent these kind of approaches, these attempts at creating QG, to the extent that they prevent these approaches from actually fulfilling that primary motivation, I said. If these problems did not prevent them from fulfilling the primary motivation, and so maybe if the theory was UV incomplete and yet did cover the Planck scale and everything that we do expect the theory to describe, then the UV incompleteness itself wouldn't be a problem for the theory of quantum gravity. Right, but I will come back to that one again in the next lecture. So as well as these problems we get from our purely theoretical attempts to combine our theories, we also have some very striking theoretical results. We have, of course, black hole radiation, ADS-CFT, and holographic principle. And then they're very striking. It's like, whoa, this is very interesting. Even though it's not a problem, it's still kind of lacking explanation. They're indications that we think might need something more to explain them. So they can be used as heuristic guides. They can be taken as indications of pursuit worthiness if you find an approach that's giving you these results. But yeah, we can then ask, how can these be used in constraining the new theory? Okay, so for the next, well, the second half of this lecture, I'll now turn to discuss the holographic principle. And this came out of some discussions with Niels and Rasmus, which we've been continuing a bit since coming here. So just as a recap of what I've said already, thinking of the problem of quantum gravity as trying to find a set of constraints and then find a theory that fulfills these constraints. Right, and we have different approaches that are doing different things towards this. So they're looking for new principles. And entropy balance and holographic principles are really being taken quite strongly in many different approaches and being used in different ways. So, for instance, people really like this as a new principle of quantum gravity, to really take us beyond our current theories. So really expressing this idea of principle theory, we've got Gardi and Siskin. New scientific ideas are usually characterized by simple organizing principles that can be expressed in a phrase or two. Invariance is the speed of light, equivalence principle, uncertainty principle. I think we should look at the holographic principle. Exact same thing being said by Basso here. Yeah, we've had principle of relativity, equivalence principle, so and so on. Then let's look now for the holographic principle. And interesting, the holographic principle is really being motivated because it's supposed to be something that's actually genuinely quantum gravitational, because it involves, matter, gravity, and quantum mechanics. And the same thing here expressed by Smolin. The first principle that's genuinely quantum gravitational. So let's look at it. Start with a bit of a, I was thinking, what's the most famous hologram? Not yet. Start with a very, very brief background on the black hole thermodynamics, because you all know it. A bit more on entropy bounds, and then the holographic principle, and then finally just some questions of where we might go. So I think of myself as being here to just not give you answers, but just stimulate your thoughts as you go for further research. Right, so the background. Black hole entropy, of course, is motivated by no-hair theorem. If you drop your cup of coffee into the black hole, entropy gets lost, and that's a problem because nothing in the black hole changes. And the second law appears to be violated. This is a problem. Also motivated, of course, by the area theorem, recognizing that the area of the black hole horizon never decreases, and this looks analogous to the second law of thermodynamics, and suggesting that analogy between the black hole area and thermodynamic entropy. So of course that suggested that the area increase here could compensate for the loss of entropy. So Bekenstein proposes that the black hole is entropy proportional to area, and then comes up with this generalized second law that's including both regular entropy of matter and the black hole entropy. And then we also have an analogous first law of black hole mechanics, which is including the surface gravity of the black hole. And then Hawking comes along, does the calculation showing Hawking radiation, in the universe with the black hole, showered with this thermal radiation, with the spectrum, again, related to the surface gravity there. So having done this, this really gave weight to that thermodynamic analogy that was being suggested. And so you can go ahead and use this to fix the Bekenstein entropy formula. The problem, of course, is that as your black hole is radiating, the mass is decreasing, the area is decreasing, and then the area theorem is no longer valid. But the generalized second law still holds. And so you expect that this puts some limit on matter entropy. So this is where the idea of the entropy bound comes from. It's an entropy bound on matter. So, right, where was I? So this analogy of black hole thermodynamics, what does it suggest? Well, of course, by analogy with thermodynamics, it would suggest that there are some microstates underlying space-time. And also that GR is itself phenomenological in the same way thermodynamics is thought of as phenomenological, and then you're motivated to look for microstates of a more fundamental theory. And the Bekenstein-Hawking entropy gives us a measure of the number of microstates, which quantum gravity is then expected to recover and explain. So this Bekenstein-Hawking result is really being treated as a guiding principle, the criterion of acceptance, and also a means of confirmation. So a very strong role that it's playing here. And of course, string theory and quantum gravity, they can reproduce this number of microstates, the entropy, under certain conditions and for particular types of black holes, but they don't have a general result on this. Okay, so that was the really, really quick background. Forgive me for that. We'll now look at the entropy bound. And yeah, another famous hologram here. So we have this entropy bound, but then what actually is the bound? Well, there are many different proposals for what the bound might actually be. And I'll just quickly go over most of these. The first one is the Bekenstein bound. This relies on Dirac process. This is where you have your matter system and you slowly drop it into the black hole. So that's the bound. And it holds only for kind of weak gravity systems. So it kind of doesn't really hold in strong gravity systems unless you're assuming some extra symmetry. Otherwise, it's very hard to apply because of this R in there. So it works. It hasn't been ruled out, but it only applies to these very special conditions. The next proposal, the spherical entropy bound, this one relies, the derivation relies on the Susskind process. So instead of dropping your matter system into the black hole to calculate this, you collapse your matter system to a black hole, and you can arrive at this bound on matter. But yeah, as you can tell, I'm not going through all these derivations. I'm following the Bosso paper on this. I'll link it. But yeah, this one relies on quite a number of strong assumptions. So Bosso suggests, well, can we find kind of a more general bound, of which this one's just a special case that holds under those particular assumptions. So The most straightforward way of generalizing that spherical entropy bound is as such. You arrive at this so-called space-like entropy bound, which states that the entropy contained in any spatial region, here, volume, will not exceed the area of the region's boundary. That's the most straightforward way of generalizing that. As you can see, maybe not, it's small. It's not successful. Why? Well, this one's not covariant, it's depending on specific slicing. There are many counterexamples to it. For example, this collapsing star. If you've got a spherical star with some entropy, non-zero entropy S, it's burning out, it's undergoing catastrophic collapse, crunching to singularity at zero, but the entropy is still non-zero. So that's obviously violating his bounds there. So we need to keep looking for kind of the correct generalized bound. So Bosco suggests, well, let's imagine this star as it's crunching down. We just take a photo of it, like a snapshot, right before it crunches. And what do we see? Well, the light that's crunching down is not going to have enough time to cover the entire area of the star before it completely crunches down. So the idea is that the area, the entropy of the area traversed by the light is always going to be less than the area of the star's surface. So he calls this the covariant entropy bound. It relies on this idea of light sheets. So basically you have a boundary here at B, and the light sheets are just, the light rays that are emanating from that boundary, but not expanding. So it's only these ones that are going in. So F1 and F3 here are light sheets. But these skirts here, the F4 and the F2, they're expanding, so those are not light sheets. And so the proposal is that the total matter entropy on any light sheet is less than A over 4. And he thinks this is the correct, most general bound. Right. So this is just his argument that the entropy on the light sheet is the entropy of the matter system, and I won't go over that. So, right. He's got this result. Okay. It appears to hold universally in nature, meaning you can't find any counterexamples to it. It's holding for arbitrarily physical realistic matter systems and arbitrary surfaces. So he thinks it always works. It can be saturated, but haven't found any examples where it gets exceeded. And it reduces to the spherical entry bound in the special case, and it implies the generalized second law. So it can directly show that the GSL holds in certain situations. Skip this one. So we have all these different entropy bounds. What do they tell us? And how should they be used in quantum gravity? So we have a lot of motivations for treating the entropy bound principle of quantum gravity. They said it's involving kind of inverse powers of h bar and g. So this is their motivation for saying it's really genuinely quantum gravitational, unlike any other principle that we have. It's surprising. It's a striking result. We've got the entropy scaling with the area when we expect it, of course, to scale with the volume according to our current theories. Bosso says that it's completely mysterious, just inexplicable according to our current physics. So taken as a motivation to look for new physics that explains this. Yeah, interestingly, Bosso really emphasizes in this paper that, yeah, we arrived at it this way, but there's no way of actually deriving it, and this is a benefit, because we can't infer it from anything else we have. So it's used as kind of indicating that we have a deficiency in our current physics. So I thought this was pretty interesting. Like, we have this principle that somehow outstripped its own motivation. You know, we arrived at it from these entropy, generalized second law, and now it's kind of going beyond that. But also thinking that black hole thermodynamics itself kind of has some strange motivations. You know, this area theorem that we use to kind of motivate this discovery is shown to be invalid by Hawking radiation. We've got the second law of thermodynamics, the regular one. We know we don't treat that as fundamental, and yet we're now kind of putting that as the part of the motivation for this. So it's a bit strange how we've arrived at this point, is all I'm wanting to say, I think. So if we can't look to its mode of discovery in order to justify this new principle, the covariant entropy bound, how is it being justified? Because it hasn't been violated in any of the calculations we've done. We haven't found anything that violates it. But these are calculations. They're remote from empirical tests. And the calculations, of course, are being based on current theories, theories themselves that we're wanting to replace. And it's standing in contradiction with them. So it's really strange to think about this. Right. So the entropy bounds imply, of course, a radical reduction in the number of degrees of freedom required to describe nature. It says that our quantum field theoretic description is highly redundant. It's just an effective description, and it's just giving us the wrong answers now. And we have tension with the principle of locality, which I didn't explain. So thinking kind of what side would we take here? How do we use this? It's a strange result. It's kind of implying that established physics is wrong. So you might think, well, we've looked for a new theory that's going to give us the correct answer. On the other hand, you might say, no, established physics is correct. New physics would give us the same answer as our current theories, and then this bound is just going to be explained by the fact that whatever the new physics is, it's going to have to recover, that's another constraint, recover our current physics. Or it might just be an artifact of no significance, like just not expect to recover it, and that we don't have evidence for thinking that it's correct. Okay. So I'll turn now to the holographic principle. And I will not talk about the information paradox, except to say that it inspired the holographic hypothesis. So the holographic principle, looking at this idea that the description of the bulk volume of space can be equivalently defined on a lower dimensional surface bounding the volume. And then the holographic principle, just frames this as a principle, saying that the full theory, the one we're looking for, can be reformulated as a theory, all of the degrees of freedom being defined on the boundary. So it's just going to put it as the number of possible states in the region of space, the same as that of binary degrees of freedom distributed on the boundary. So this is the holographic principle. It has a concrete manifestation, concrete theoretical manifestation in the ADS-CFT duality. So the ADS theory, of course, being string theory in a d plus one dimensional ADS spacetime. So that's your bulk theory. That's your theory with gravity. and then the idea that it's dual, so somehow being equivalent to the CFT without gravity, being defined on the boundary of the case. And yeah, this is important because it's taken to be an exact duality and not just valid and perturbative approximation. So there are different kind of conceptions of the holographic principle. Like Bosso thinks that the holographic principle is the claim that kind of the origin of the entropy bound, the covariant entropy bound that discovered, is to be found in the new theory. Smolin takes it as, the entropy bound gives us that limit on the number of degrees of freedom, but the holographic principle is supposed to tell you something about the nature of those degrees of freedom, namely that you can explain the bulk theories and measures of geometry in terms of the boundary theory and measure of information. So, I have motivations for using the holographic principle as a principle of quantum gravity. Well, it's depending on how you're going to frame it. But yeah, it's motivated by supposedly solving the information paradox, but also because it's supposed to give an explanation of that mysterious entropy bound. But to me, this suggests that the real principle is the entropy bound. That's what's trying to be explained by the holographic principle. So not the duality. Okay. So, did I go one? Yeah. So Rasmus and Niels have looked at the relationship between entropy bound and the holographic principle, arguing that the entropy bounds are intra-representational, meaning it's applying within one theory. Obviously, we're describing entropy bounds on matter and the black holes, and that's within the one description, the one world. Whereas on the other hand, we have the holographic principle, which is inter-representational. So it's relating two different descriptions. We've got the description on the boundary and the description of the bulk. So how can then the holographic principle, giving us the entropy bound on the bulk theory, how can it motivate or explain that entropy bound? And asking kind of, what can we say beyond this? De Haro has distinguished between the theoretical and heuristic function of the duality. So if you're looking at the dualities, the theoretical function is kind of looking for some common core theory. So what's in common in the two representations, and trying to just learn about that. But the idea is that in doing that, you're not actually learning anything about physics beyond, because you're only just learning about that duality relation. The idea, if you want a new theory beyond that, you somehow have to break the duality. So you want a theory that's going beyond that common core theory. You break the duality, you find a more fundamental theory, or use it to find a more fundamental theory, and then you can show that the duality gets recovered approximately in something, the idea. Right. So Rasmus and Niels have kind of questioned this. Well, a similar thing. First, the holography itself being intra-representational, it can't tell us anything outside, so beyond the duality. So what you want to do is actually render it intra-representational. So working within a single description here. And then we can have a heuristic use of the duality in this way, to try and render it within one world, basically. You know, like if you're working on the ADS side, you've got the world with gravity, but then you don't have your QFT, basically. And if you're working on the CFT side, you've got your quantum description, but you don't have gravity. So the idea is that you can't really learn much when they're separate. The idea is to embed them both within the one world, so you can actually get access there. So here, say, you wouldn't need to recover the duality or break it. Okay. And yeah, presents this as an example of this is in the Ryu-Taganonaki formula, which, you know, is coming from the ADS-CFT, the entanglement entropy. And you look at this and it's like, yeah, well, we've got the formula, we've recovered the entropy. But actually this isn't the black hole entropy, because it's an inter-representational description. So you've got the entropy, but that entropy is living on the CFT side. It's not living inside with the space-time, whereas this area is on the other side, it's in the other description. So they argue that then you can't use this to explain the origin of the area in terms of the entropy and vice versa. Because in the representation where the area exists, the entropy is not there, and where the entropy exists, the area is not there. So even though this looks like you've explained the black hole entropy, you haven't. Okay. Sorry, that was super quick. Direct any questions to Rasmus, please. So I'll just finish with some kind of summary and suggestions for you on future work. So firstly, how are the entropy bounds in quantum gravity, and how should they be used? Well, the entropy bound, that covariant one from Russo, it's being used in string theory as a guiding principle. It's kind of motivating quantum gravity as a theory of microstates. It seems possible you could use it as postulate, like just laying it down as part of the theory. Can it be used as a criterion of acceptance? Well, I think this is open. So the criterion of acceptance is very strong. It means you won't accept a theory unless it actually derives this result or is consistent with it. So you can ask, well, which entropy bound, and do we need an explanation of it? Like, is this really a constraint on the theory? Must we predict the number of microstates? Can it be used as means of confirmation? Yeah, in causal set theory, they've recovered the spherical entropy bound, and so you can think, well, this is indication that the theory is on the right track. It's giving us some degree of confirmation. What about the holographic principle? Well, yeah, it can be used as a guiding principle. You follow the Haro. It might involve the inexactness of the duality. You have to break it. Or we can look at this transformation into an intra-representational picture, following Linnemann and Jackson. Can we use it as a postulate? Some people do. They really take this as the cornerstone of any theory. So it says criterion of acceptance. I'm not sure how you do that. And yeah, it's being used as a means of confirmation already, of course, in string theory. Okay, so that's it. Summary. I've looked at kind of different roles of principles in quantum gravity, being guiding principle, criterion of acceptance, postulate, means of confirmation. Looked at entropy bounds, being motivated by this, idea that they're genuinely quantum gravitational. It's somehow super surprising and mysterious, that we can really use them in all roles listed here. But the problem, of course, which is actually the correct entropy balance. The holographic principle, on the other hand, it's motivated by its potential to explain the origin of the entropy balance. But can it actually be used in these different roles? Not as it is. You'd have to kind of break the duality, because that's what's kind of keeping you locked into those fields. So you can either render it inexact or, again, transform it into a symbolic representation. And, yeah, finally, the suggestion that entropy bound is the principle to look at in quantum gravity rather than the holographic principle. So, thank you.
All right, thank you very much. Emily.
Hi, yeah, thank you. That was a very interesting talk. So the holographic principle is really simply described in sort of terms of the spatial areas and volume, like within a spatial dimension. But I mean, the Rousseau bound, the entropy bound we currently think is correct, seem to not really be about areas and volumes and more temporal, think about information systems and surfaces and so on. So does that kind of affect how we should think about the holographic principles? Is that a problem for them? Could we be updating them to reflect that?
Yeah, I think he does tie them together in the paper. What did I say? That kind of can use the holographic principle to explain it in some cases.
You can when the stuff inside is sufficiently static,
Yeah,
right?
exactly.
Then it will cross the whole
Yeah.
area volume. But that seems to be not fundamental, right? That just it reflects that case.
So, yeah. Yeah, I don't know what to say. I think you're right then. You kind of look, if you're taking that as the right bound, then it would kind of motivate something.
David?
Thinking about this last set of arguments about significance, I mean, here's a concern. The way this is set up looks as if it's thinking, okay, how do we go beyond where we are at the moment to a deeper theory on the basis of this duality or the holographic principle or whatever? But I take it from the point of view of people who, like ADS-CFT-based approach to quantum gravity, then at least if the system I'm studying is appropriately described with anticipated boundary conditions, I don't need a deeper theory of gravity because I've got it already. I'm done. My task is to explore this extremely rich theory and to wonder how it generalizes. But it's not as if I think, in these lines, that ADS-CFT is an approximation to a deeper and better description of anticipated quantum gravity. ADS-CFT is a deal. Now, if you think back to the development of ADS-CFT, then of course you are looking for how these dualities are going to be useful and helpful. But then it seems that would seem the place to test some of these ideas. I mean, was it the case, in fact, that when people went to ADS-CFT, it was the entropy bound that was the useful principle, was it duality that was the useful principle?
Yeah.
There's sort of two halves there, I suppose. There's a question, how do we think about this now in the context of ADS-CFT as a putative complete quantum gravity theory? And how do we think about these principles as applied to the kind of complex discovery of ADS-CFT?
Right. So the first one, you mean, is this the theory of quantum gravity? People would work on that and say, look within the duality to just develop the theory.
Yeah, well, the theory of quantum gravity for systems with asymptotic ADS boundary conditions.
Yeah. Rather than needing to motivate this deeper theory that would require going forward. Yeah, I mean, I think that's totally fair. So I guess I would say then, looking back at that kind of primary motivation, does it fulfill those kind of constraints? And if it does, then it could be a good candidate. If not, then you would look for something more beyond. And that's the weird thing, if it itself doesn't kind of motivate you to look for something beyond, then you need those external reasons for seeking a deeper theory. And yet we're kind of taking this as, we're hoping this is an indication of it, because it's such an interesting result that we can play with. But in order to actually use it to find something deeper, you kind of have to break it. So yeah, I think it is strange in that way. Yeah.
I mean, to follow up slightly, perhaps I slightly misspoke when I say it's ADS-CFT is the final theory. I mean, ADS-CFT doesn't specify theory. ADS-CFT is a general term that quantum gravity theories and asymptotic and de Sitter space-time are dual to conformal field theories on their boundaries in generality.
And then you find theories that...
Yes, so from that point of view, if that's right, and if we suppose for the moment we are considering systems with ADS boundary conditions and we don't know about cosmology, then you'd want to say, okay, I don't actually want a deeper theory than ADS-CFT, but what I want is to find the particular theory. One of the really useful things I've learned about the correct quantum gravity theory for this thing is that it obeys ADS-CFT duality, supposedly. So then, but then from that point of view, in a sense, the value of the duality is going to be, semi-pragmatic. It's like it's mysterious how to think about theories of this kind, and therefore the ability to move between different ways of describing them is going to be useful in exploring the shape of those theories and trying to work out which particular ADS-CFT theory is going to be the correct theory to be applied to our universe.
So it can play a heuristic role in that sense. Yeah, definitely. That's good. Yeah. So what was the second?
The second was the thought. I mean, so if you buy what I was saying first, then we're not currently, people doing ADS-CFT quantum gravity are not currently in the business of looking for a theory that's deeper than an ADS-CFT theory. But of course they were in the process of looking for that in the 90s. So it would be interesting to ask, okay, given the various sort of things that looked like they were duality principles or holography principles were certainly described as being highly motivated, people like Schrödinger and Alcina and written in that period. It would be an interesting, this is like a suggestion for someone to think about rather than a need to Karen has to tell me the answer right now. It would be interesting to take these ideas and look at that period and ask, okay, what were the actually useful motivations for developing ADS-CFT duality in the 90s?
Yeah. Thanks.
Mike has a finger.
Yeah, I guess the most immediate part of the finger was saying David's own clarification of David in the previous back and forth. Slightly more generally, though, still in the same theme. And throughout the talk, I sort of, this is going to sound grumpy, it's not grumpy. I kind of feel like principles are just like less courageous versions of models. Or it's something like if it's a principle, you can just always maybe default back to heuristic, or you can say, well, it wasn't complete specification, so it was just hand-waving this other not heuristic sense, but just in a vague sense. And then I feel like interesting uses of these principles come up exactly when they start being taken more seriously as
constraints, right? Yeah.
Right, as constraints for toy models and so on. Is that like a virtue? That's why I say I phrased it in a grumpy way. It's less courageous models.
I mean, I'm taking a very, very broad kind of understanding of them. But I guess, yeah, I mean, for heuristic, of course, you can use anything heuristic. But I think this criteria of acceptance is perhaps the more interesting one. Like, what must the theory be like in order for us to accept it? And I'm thinking things like, I thought the most basic one was kind of the recovery of GR, or the emergence of space-time, like some sort of correspondence between quantum gravity and GR, right? So that's certainly a constraint on the theory. If we don't get, we can't show that it's consistent with GR by doing this, then it's not going to be accepted. And that's kind of what a lot of the approaches now are really fixated on, right? How do we recover GR and space-time from our theories without space-time fundamentally? So that seems to be a very, very strong constraint as a criteria of acceptance. Using correspondence principle, I guess. But then I was also thinking, well, kind of what's even more basic than that. It seems like the principle of consistency. Like starting off, it's being motivated by this kind of perceived inconsistency between our two theories. And within our theories, physicists complaining that their divergences are making it problematic or self-inconsistent. So that also can be used to put constraints on the theory. I think going even beyond just kind of the heuristic aspects, like we really trying to pin down what would be acceptable on the theory. Yeah. But yeah, the relation with models, I don't know.
The reason why I was related to David's line is, it seemed, this might be folk history, so I might not have a quick grip on it, but it seemed so immediately and immensely more productive or germane or whatnot to think of ADS-CFT as seriously telling us about the sector of quantum gravity that is asymptotically anti-excited. Like that seemed like so much more productive than the vaguer, we're getting a sense that holography is a compelling way of thinking about the problem of quantum gravity.
So you think just kind of use it rather than question it?
That's the
Yeah.
so it might be foolish or foolhardy, but yeah, just sort of embracing running with it and seeing how it runs into the ground was just but that's models and theory.
Yeah. I mean, this is of course a good thing to do. Like, do everything you can to explore these different aspects. But I think it's also interesting and important to know why you're chasing after it in a way. What can it tell us? We can do some interesting philosophy there. Before you pour all your resources into doing this, maybe it is good to step back. So I guess, we could go back to what Chris was saying in the talk just before this, and maybe we shouldn't, put too much in these kind of principles rather than seeing where the physics takes us. So yeah, that's valid. Yeah, I don't really have a reply.
Okay, we have a long list of fingers. Rasmus.
Yeah, it's a finger going in entirely different directions. I think let's stick with the fingers that are sort of in this general area.
Okay, then maybe Enrico's finger.
Okay, so yes, I actually wanted to go back to the first. I actually wanted to go back to the first question that David asked. Thanks for the talk. So I just very briefly, I just wanted to maybe push back a bit on this idea that if you have ADS-CFT, right, then you have solved like gravity in ADS space-time, right? Because that is true in a sense, but there seems to be something that you could still want out of your quantum gravity theory, even if you have ADS-CFT and you believe it is correct, in that you presumably do not want whatever your definition of quantum gravity is to depend on just boundary condition. So you presumably would want, you could still use this as some kind of like principle to look for a deeper theory, and as you would want a theory that, given a choice of boundary condition, looks like ADS-CFT in ADS boundary conditions, but is not necessarily limited to ADS-CFT. While ADS-CFT currently, if you just change the boundary conditions, then you're left with nothing, right?
So there was a reason I kept qualifying it as long as we have ADS-C.
Oh, okay.
And so in that sense, I kind of agree. I mean, he's just a slight modification of that. I mean, I think in ADS-CFT, the ADS is just an infrared regulator. I mean, if I'm looking at an isolated system, I need to regulate it in the infrared anyway. It's harmless to say I'll regulate it with an arbitrarily small negative cosmological constant. But what I won't give you is cosmology. I mean, I think one statement you'll hear there is that since ADS-CFT, we have satisfactory quantum theories of gravity, but we still lack satisfactory quantum theories of cosmology. I'm not saying endorsing that claim, but I think that's a good sociological description of what people think.
So David, was that your finger also?
No, mine was just really quickly back to on the debate here. Since there's a queue, let me leave it and I'll pursue offline. I don't want to get away students.
Okay, yes. Sakshi.
Oh, okay, so...
No finger, new question.
Yes, new question. I'm sorry, Karen, this is more of a general question that integrates what
Love
you
it,
said,
do it, yeah.
what David said, and what Mary has said earlier today. I don't know if she's here.
She's
Oh, there you are. So I remember you saying that you interpret interpreted ADS and CFT correspondence to mean that neither of those theories are fundamental if we want to.
No, I didn't say that neither of these theories are fundamental. I just said that the space-time we described, because there is an equivalent between neither of the theories is fundamental, and therefore it's an emergent flow, and it should be an emergent. And we discussed about that a number of times. I didn't say that the approach are not fundamental. I said that people will get the kind of correspondence between these two approaches and I say which one we think is fundamental, and that's why I say it's an emergent space-time and we are.
Okay, I'm not sure I fully understood. Okay, so maybe that would be better to wait.
This corresponds with that. I cannot say that this is fundamental or that is fundamental. Therefore, it's emergent.
Right, exactly. So you said they both were kind of emergent, if I understood.
No, there's nothing both emergent. I'm saying space-time is emergent.
Space-time is emergent. Okay.
I'm not saying that the theory is emergent. It's emergent.
Okay, okay. So I guess my question was, because from what you said, David, it seemed like, would you privilege the ADS part of the correspondence as giving you the theory of quantum gravity? You wouldn't say that.
I totally relax about dualities, and
Yeah.
I don't feel any obligation to say which half of a duality is fundamental, or any obligation to find some other theory such that both of them are representations. I'm perfectly happy to say, look, here's a mathematical structure I can describe this way, or dually this way, and that will still.
Then what's the
This is
ontology?
I am unmoved by that question.
Okay, so I was wondering if, Karen, you had anything to say about whether the entropy bound, implicitly says something about the ontology, and how we can think about making the holographic principle intra-representational, and I think that's a big question, and that's exactly what I've also been thinking about.
Yeah, exactly. Like, it seems like we have this, really cool result, and we're already kind of have it in our head that we want, high energy, usually complete, quantum theory that somehow relates to gravity. And then we have this result that's so tantalizing to give us this, and yet to actually use it to show that space-time emerges, we have to kind of break it somehow or render it differently. We have to kind of force it in a way. So, yeah, I'm just kind of tempted to say maybe this isn't it. Like, maybe we've kind of got it in our heads that we want this more fundamental description in terms of the micro degrees of freedom. That we're kind of putting that in and saying, well, that must be the fundamental one, and we must somehow modify this to get out the space-time. So, yeah, it just seems a bit weird to me. It seems like we're kind of we're getting really invested in it, right? Because it's, seeming to give us what we want, but at the same time we're kind of forcing it to give us what we want. So I'm really not sure about that. Yeah, really good question.
It's just a comment. Can you go back to that slide on constructive versus principle theories?
Yes.
Just a comment on that related to what role the principle should have.
What, the Einsteins?
Yeah.
Mm-hmm.
Yeah, just a comment. So there's this distinction that he made between constructive theories and principle ones. But he says that the fundamental theory is a
Constructive one, yeah, exactly.
And so but you want to construct the fundamental theory on solid ground. But what are these solid grounds? Well, first you get the principle theory. On the principle theory you get postulates that will be empirical, right? Empirical facts. And from those empirical facts you derive a principle that will serve as constraint for the constructive one.
Yes, thank you for bringing that, because I should have mentioned that, and that's perfect, because then it's showing how you can tie them together and still use the principles in doing it.
Yeah, that's how especially special relativity is a principal theory that should be satisfied by the constructive one. In a similar way, he derives the quantum, the light quanta, and he sees it as a constraint that the constructive theory should satisfy.
Yeah, nice. Thanks. Very good point.
Dominic.
I mean, the way David expressed the duality just then seemed to make my question clearer to me. Seeing as these are just can be construed as different descriptions of the same mathematical structure, perhaps. It seems to me that the holographic principle, when applied to these whole theories, is quite a different principle to all the ones we listed before. Because, I mean, the speed of light is constant. If I have a theory which doesn't have that in it, then there's a problem. Right? But if I had just got ADS and got a completely effective description of the ADS side, I knew nothing about the CFT side of the duality, I've still got the theory. And so, I mean, as a tool for doing calculations, as like an actual practical tool in a physics toolbox, it seems useful. But as like a principle that's inside our theory, it seems like quite a stray. It seems at least very different to all of the principles.
But like, if it's being used to explain kind of the nature of those microstates.
Yeah, if it's being used to explain the black hole information products, it does that well. I agree that's a good example inside the theory, but I'm talking about like quantum gravity as a whole. When use that.
Like how we could actually use it. Yeah, please.
Yeah, so at least I think there's a sense in which you could say, just as you were saying, we want a theory that has a certain bound in the speed of light, we say we want a theory that has this property of being re-representable in a theory that has one less dimension. And I agree that seems to be a very severe constraint to please, but you could in principle impose it in much the same way as just saying that is whatever mathematical formalism I'm now using to describe what would be my higher dimensional theory, I want it to be in such a way that I don't put more degrees of freedom in there that I can't do this re-representation in a lower dimensional theory. I don't know, maybe relates to the information paradox, you might have reasons to do that kind of thing, but I don't see this sort of a principal reason why you couldn't implement such a principle.
Chris, thank you very much for your patience.
Yeah, so this is somewhat superseded by some of the other questions, but just to think in a kind of historical analogy, there's principles that I think there's at a coarse-grained level agreement about what they mean and how they help to lead to a theory. So I'm thinking of the equivalence principle here. But at a fine-grained level, you'll find plenty of philosophers who say there's no such thing or have very strong disagreements about what it could mean. And so I'm wondering, like, how that kind of case compares to the case you're looking at. So I mean, I realize it's just harder because you don't have the historical perspective. But is it the case that the people involved in the 90s, before you got ADS-CFT, just like really fundamentally disagree? Or is it more like special cases that might, so if you look at the entropy balance, for example, were they sort of explicitly thinking like these are all possibly subsumed by some more general formula that we just haven't come up with yet, and so you could see them as sort of steps along the way, or is there? I just didn't get a clear sense of like the sort of scope of disagreement in your analysis, and how that played into the heuristic role that the principles were playing.
Guess I'm not really sure. So they thought there should be an entropy bound based on those considerations from the black hole thermodynamics, and then went about trying to find it. And then thinking that it's giving us some indication about the quantum nature of space-time, right?
But should we think of it as like a series of special cases? Like you start off with construction and you realize, oh, well, that's not covariant, so I should
Sorry,
And so
that's how it
then
happened.
in each case, you sort of see the other one as a special case of the previous one that they're sort of subsumed.
For
And then
some
at the
of
end
them
the day,
it
you have
was, and some of them are very disagreeing. Yeah. So there was that other one I didn't mention as well, Smolin, and he thinks that's the correct one. So yeah, they're still fighting a bit. Yeah. So some of them have motivated the more general ones, and some of them are just different. Yeah.
David, did you have another question or comment?
Many. Lots of bits and
We
pieces.
don't have all that much
So
time.
nothing that I can't follow up in there.
Maybe one more then?
Emily's also got a question.
Oh, okay, I didn't see that, sorry. Emily.
So sort of naively it would seem to me that because in the ADS-CFT construction you have this exact pattern between the bulk and the boundary, it sort of seems like the strong versions of the entropy bounds are true in that construction. Is that
They are. Sorry, what?
Seems like the really strong versions of the entropy bounds are true in the ADS-CFT construction?
True?
Correct.
Yeah. I mean, I'm not super expert on this. I'd have to look at it again, so I'm not so sure. But I think that's the way they're putting it forward.
Yeah, because it seems to me like, in a sense, the construction depends on the claim that those strong entropy bounds are true. And I wonder if that then it gives some cause for pessimism about the same kind of construction working in the real world, given that we know those entropy bounds are not true in the real world.
I'm not sure. No.
Okay. I suggest you join me in thanking Karen once again.